My name is Dr. Vladislav Steyman, and I would like to present our new research analysis of Holey Photonic crystals with coupled mode theory. The object of the research are electro-optical components, namely optical fibers and semiconductor lasers, confining light by periodicity of holes in dielectric media, so-called Holey Photonic crystals. Here you see examples of Holey Photonic crystals, microstructured fibers, both hollow core and solid core, and hollow resonant microcavity based photonic crystal laser. The research was conducted by me, Dr. Vladislav Steyman. I am with the Electrical Engineering Department of Ort Brawley College, Carmel, Israel, by Professor Eli Capon from the Physics Department of Swiss Federal Institute of Technology, Lausanne, Swiss, Professor Amos Hardy from the Electrical Engineering Physical Electronics Department of Tel Aviv University, Tel Aviv, Israel, and our students, Lidor Giladi from the Electrical Engineering Department of Ort Brawley College, and Yelena Smith from the Electrical Engineering Department of Ort Brawley College and Electrical Engineering Physical Electronics Department of Tel Aviv University. The purpose of the research was to develop a new method allowing application of coupled mode formalism to analysis of optical characteristics, namely array modes and photonic band structure of Holey Photonic crystal devices. This work received Best Student Paper Award at the International IEEE Convention of Electrical and Electronic Engineers in Israel at 2040. Part 1. Theoretical background. Coupled mode theory. Guided modes of a photonic device. Let us consider photonic device composed of Ny by Nx coupled waveguides or lasers. The light is confined in xy plane and propagates in z direction. Assume that all individual guided modes of all solitary waveguides or lasers are known in advance. The question is, how can we compute guided modes of a whole device, so-called array modes? One of the ways to do that is by using so-called modes expansion conjecture. This conjecture states that transverse component of array mode propagating along z-axis is nothing but linear combination of transverse components of all guided modes of all individual waveguides multiplied each by its partial amplitude. Let me show you how it works. Assume we have a square photonic array of 11 by 11 single mode identical waveguides. In this case, Nx equals to Ny equals to 11. Each waveguide supports for one mode only. We assume that guided modes of all solitary waveguides at all the sites as well as their propagation constants are known in advance. Here you see example of a fundamental guided mode of a solitary waveguide. We are to find a envelope function, or in other words, a set of partial amplitudes U0, including all partial amplitudes of all individual waveguides, and propagation constant of the array mode, sigma. if we will find u0 and sigma, we can reconstruct the full array mode et as a function of x, y at the initial position z equals to 0 with the modes expansion conjecture. Standard coupled mode approach for finite arrays states that in order to find envelope functions u0 and propagation constants sigma, we need to solve so-called coupled mode eigenequation. Matrix M times u0 equals to sigma times u0. Matrix M is called coupling matrix, and it contains all the individual propagation constants and integrals of overlap and exchange between all the guided modes of all the solitary waveguides. Clearly, u0 is the eigenfunction of M matrix, while sigma is its eigenvalue. There is another way to approach the problem of array modes. For large photonic arrays, where nx and ny tend to infinity, one can assume periodic boundary conditions, or equivalently, that envelope functions of array modes u0 are plane waves, defined only by their dominant spatial frequencies, namely kx and ky, being also components of array mode wave vector, and therefore are known in advance. This assumption leads us to so-called extended coupled mode formalism, being a kind of combination of a standard coupled mode formalism for finite arrays and a kind of plane wave expansion. In order to compute array modes with extended coupled mode approach, one should solve a so-called extended coupled mode eigenequation. Matrix M double underlined, which is currently a function of kx and ky, times u0 double underlined equals to sigma, which is also a function of kx and ky, times same u0 double underlined. Here, M double underlined is extended coupled matrix, which contains all the individual propagation constants and overlap and exchange integrals between all the guided modes of all the individual waveguides of a central unit cell with their neighbors. Kx and ky are components of a wave vector from the first Brillouin zone. Alternative view, these are dominant spatial frequencies along x and y axis of an array mode. Sigma is the propagation constant of array mode. It is eigenvalue of M double underlined. u0 double underlined is a set of partial amplitudes of individual guided modes inside the unit cell of the array. Now, there is a mandatory requirement for application of coupled mode formalism. This requirement states that for any individual element, waveguide or laser, n core should be larger than n clad. For this reason, Holey Photonic devices for which for a solitary element, namely a hole surrounded by dielectric material, holds n core is smaller than n clad, till now were not considered as objects suitable for coupled mode analysis. Part 2. Application of coupled mode formalism to Holey Photonic devices. There is another way of looking at a periodic array of holes. Square lattice of holes can be considered for the same extent as a square lattice of quadrangular spots. Square lattice of ny by nx holes should be seen as a square lattice of ny plus 1 times nx plus 1 quadrangular spots. A unit cell of the array is a solitary dielectric spot surrounded by air. Furthermore, hexagonal lattice of holes can be considered as a honeycomb superlattice of triangular spots. In other words, periodic sequence of two triangular spots. A unit cell of this array, also called a supercell, is two dielectric triangular spots or two waveguides, spot up and spot down, surrounded by air. Consideration of a Holey Photonic array as a periodicity of dielectric spots surrounded by air holes meets the requirement n core is larger than n clad, and thus allows us application of coupled mode formalism to Holey Photonic devices. The advantages of the approach. First, accurate numerical computation of optical characteristics of Holey Photonic devices. A full set of array modes and photonic band structure can be done very fast, a few tens of minutes for finite arrays and 2-3 minutes for infinite arrays on a standard PC machine, 100 to 1000 times faster than with the majority of the widespread approaches. This advantage in computation time, combined with high accuracy of the calculations, can be very useful in particular for engineering design and optimization problems. Second, for infinite arrays, analytical prediction of the number of photonic bands, the upper and lower limits, and consequently bandwidths becomes available. Regarding the Holey Photonic crystals, to the best of our knowledge, those analytical predictions become available for the first time with the extended coupled mode formalism. The limitations of the method. Clearly, our approach has limitations. It is accurate until there are guided modes supported by the spots, and there are no guided modes supported by the bands, or in other words, until the electromagnetic fields of array modes are localized in the spots. The range of the hole diameter to pitch ratio suitable for application of our method should be found numerically for a specific device. Nevertheless, it is not limited by a hole diameter to pitch ratio close to 1. The reason is that the guided modes of the solitary spots and bands as well can be found only numerically, and the result depends not only on the hole diameter to pitch ratio but also on the core-clad contrast and the injected wavelengths. Note also that even above the suitable range of applicability, namely when individual veins become to support guided modes, the results acquired with our method remain correct. They simply become incomplete, since the additional array modes originating mainly from and localized mainly at the veins will appear. In order to accomplish the analysis, one should account for those vein localized array modes as well. Part 3. The benchmark. As a benchmark, we used well-known Helmholtz equation. A second derivative of the transverse component of the array mode electric field plus k0 square n square times the transverse component of the array mode electric field equals to sigma square times the same transverse component of the array mode electric field. Here n is the whole array refraction index distribution in xy plane at the position z equals to 0 or at the entry plane. It is known in advance. K0 is a wave number which is equal to pi over lambda 0, where lambda 0 is the injected wavelength. It is also known in advance. Transverse component of the array mode field, as well as propagation constant associated with this transverse component, sigma, are unknown. Two notes. First, we solved Helmholtz equation in finite differences. Second, as opposed to coupled mode theory, which requires decomposition of a dielectric function of a whole array onto dielectric functions of individual waveguides, Helmholtz equation treats an array as a single non-uniform waveguiding structure. Thus, the results, namely the fields E and propagation constants sigma, acquired with the two methods, should be completely independent. Photonic band structure. When the spatial distributions of the array modes and their corresponding propagation constants sigma are found either with coupled mode theory or with Helmholtz equation, it becomes possible to compute photonic band structure. To do this, one should find the kx and ky coordinates of maxima of Fourier transform of each of the array modes. Then one should make correspondence between the propagation constants sigma and the location of those kx ky coordinates in the K space. Part 4. Results and discussion. As it is usual in fiber optics, we used effective mode index, namely n effective, which is equal to sigma over 2 pi over lambda 0 for array modes and beta over 2 pi over lambda 0 for modes of solitary spots, instead of propagation constants sigma or beta correspondingly. As a first example, let me show a square photonic array of 12 by 12 dielectric spots. Here you see effective mode indices of array modes as computed by coupled mode for finite arrays, coupled mode for infinite arrays, and Helmholtz equation. For coupled mode approaches, we used a quadrangular spot as a unit cell of the array. For Helmholtz equation, the whole array was considered as a single non-uniform core waveguide. Here you see photonic band structure of the same array. It is shown along high symmetry lines of a square lattice, gamma x, x, m, and m, gamma. Once again, note a close agreement between the different methods. As a second example, let me show you a honeycomb Holey array with 7 holes at the outer side of the hexagon. Here you see effective mode indices of array modes as computed with the standard CMT for finite arrays, extended CMT for infinite arrays, and Helmholtz equation. For coupled mode computations, we used two dielectric spots, spot down and spot up, as the building blocks of the array. For extended coupled mode computations, this pair, spot down and spot up, was considered as a unit cell or supercell of the array. For Helmholtz computations, all this structure was considered as a single non-uniform core waveguide. As you see, there is a close agreement with the results acquired with the three methods in case of honeycomb array as well. Here you see photonic band structure of the same array shown along high symmetry lines of the hexagonal superlattice, namely gamma L, L, X, X, gamma. As you see, there is a close agreement between the results acquired by the three approaches. Now, the majority of real Holey photonic crystal devices are based on defects in periodicity of holes. The question may arise, is the development above for perfectly periodic arrays applicable to analysis of real Holey photonic devices based on defects, such as the one shown here? The answer is yes. Note that the answer yes was general. As a particular illustration of this general answer, let me show you an example of a band structure analysis of a finite hollow core fiber. This fiber was analyzed with the Helmholtz equation. We compared its band structure with that of infinite honeycomb array computed with the extended CMT. As you see, there is a close agreement between the band structure of the perfectly periodic array and that of the real photonic crystal device with introduced defects. This is a very general result. Introduced point defects, such as those you see here, don't change the photonic band structure. Conclusions. First, applicability of coupled mode formalism was extended to include Holey photonic crystal devices, both devices based on perfectly periodic photonic arrays and those with introduced defects. Second, in the range of applicability, our approach allows fast, minutes about 100 times faster than most of the widespread approaches, and accurate evaluation of optical characteristics, array modes, the associated propagation constants, and photonic band structure of Holey photonic devices. Here you see a list of references published and submitted for publication, articles related to this our research. Thank you for your attention.